So when chemical reactions happen, the reactants react to make products, and there's always a change in heat, delta H or delta E. And it's that change of heat. You can calculate many different ways. We've done many different ways before, through calorimetry, through heats of formation, multiple other ways. What it boils down to is change in heat is because bonds of the reactants are broken and they reform into new bonds as products. For those bonds that are formed, energy has to go into them. So we put energy into bonds to break them. And when they reform in the products, those bonds release energy. So you have energy going in and then energy coming out. And now the energy going in, energy coming out, those are almost always two different values. So you have a differences in heat values. That's where you get your delta H. That's where you get your change in heat, which is your heat of reaction. So the heat needed to either break bonds or the heat released by bonds forming, that is called bond energy. So every type of covalent bond between two atoms, there's a certain amount of energy needed to either break it or form it. Right? So the technical definition of bond energy is energy needed to break 1 mole of a covalent bond. So like here we have a carbon-carbon bond. So anytime you see a carbon-carbon bond, you have to add 347 kilojoules per 1 mole of those carbon-carbon bonds. You have to add that much energy in order to break those bonds. Now, breaking bonds is always endothermic, right? Which means that the bond energy is always going to be a positive value. But what that means is if you're forming a bond, so if two carbon atoms come together and are formed, they're going to release that same amount of energy. So it's going to release 347 kilojoules per mole. So again, the bond energy for a carbon-carbon bond, 347 kilojoules per mole is added to break the bonds. 347 kilojoules is released or given up when the bonds are formed. Now, if we look at every single bond in the reactants and every single bond in the products, and look at all those bond energies, we can combine those mathematically, and we can figure out the heat of reaction of any reaction we're looking at. And to do that, you do this little equation here at the bottom. All right, the heat of reaction is the heat, or the sum of the heat of the bonds broken, which are the reactants, minus the sum of the heat, or the sum of the energy of the bonds formed, products. So reactants minus products. Now, this is an example of a table of some bond energies. On tests or whatever, you'll be given these data, either this table or just the selected data that you need. As you can see, there's a whole bunch of different bond energies, whole wide range of values. Now, one thing to note here, if you look here, carbon-carbon single bond energy is 347 kilojoules per mole. If you look down here, carbon-carbon double bond, 614. Okay, it's not exactly double the carbon-carbon single bond. So just because you have multiple bonds doesn't mean that the number is going to be an exact multiple, 2 times, 3 times, whatever. Okay? So just kind of keep that in mind. You have to look up the exact, whatever type of bonds you have, look those up when you look up these values. It's not calculated. All right, it's pretty easy. So here we have this, reaction here, and we don't have your textbook anymore, so we don't need the bond energy page. So get rid of that. All right. So what we have here is we got this reaction here. And in order to figure out delta H, we need to figure out all the bonds for each of these molecules, each of these compounds. With this, typically you're going to have to do the Lewis-Stott structures for these. So, for example, if you look at CH4, and there's your CH4, and that's plus 2 Cl2s. All right. So by doing this, we can see all the different bonds we have to work with. F2, So 2F2s yields CFCl2. So we got a carbon with 2 CCl bonds and 2 CF bonds. 2HF, so HF. And then 2HCl. So there you go. So what we gotta do is gotta look up here's the bond energies. I just pulled these off of the chart and wrote them here. Just so we just have just the ones we need. So we're gonna take all these bond energies and figure out each of the bonds here and then calculate the heat of reaction. So here we'll look at CH4. So here's our CH bond, 413 kilojoules per mole. And since we have 4 CH bonds, it's 4 times 413. ClCl, where's that? 239. We got 2 of them. Plus 2 Fs. Look over there, it's 154. All right. So that's all your reactants. So that minus, and we got 2 carbon fluorine bonds, so 2 times CF. So if I look here, it's 485. Plus 2 CCl bonds. I see that's 239. Plus 2 HF bonds, so 2 times HF, it's 565. Plus 2 HCl bonds, so 2 times, where's HCl there? It's 427. Okay, we're going to add all those together. All right, so if we add all those up, doing their calculator real quick, you should get 2438. Add up all those, you get 3632. All right, so these are your bond energies for your reactants. These are bond energies for your products. And it's reactants minus products. So you subtract that. And you get your heat of reaction as negative 1194 kilojoules. So this reaction is negative 1194 kilojoules. That's your heat of reaction. So simple enough. That's how you do calculating heats of reaction just using bond energies. Just remember, it's reactants minus products. Every other type of heat calculations you've done products minus reactants or final minus initial. This is the twist here. It's reactants minus products, or initial minus final, if you want to think of it that way. So the order is a little bit backwards than everything else you're used to. So just keep that in mind. Other than that, it is a pretty easy problem. And there you go. That's calculating bond energies.